all participants. I, Prasant Pandey, welcome all present here to the third day of ETP 2024 Emerging Trends in Photonics. Today's first technical session will be taken by one of the emerging researcher in the field of antenna design and microwave, Dr. Anand Sharma sir. Dr. Anand Sharma sir have obtained Bachelor of Technology from UPTU in 2012 and Masters from JP University of Engineering and Technology Guna in 2014 and PhD in RF and Microwave Engineering from ISM Dhanbad in 2018. After that, he joined our college, Rajki Engineering College Sonbhadra, and served as Assistant Professor in Electronics Engineering Department. And after that, he was selected in MNIT Allahabad as Assistant Professor in June 2019. Currently, he holds the position of Assistant Professor in Department of Electronics and Communication Engineering, Motilal Nehru, National Institute of Technology, Allahabad, Prayagraj. He has published more than 60 articles in international SCI indexed journals and also presented more than 40 articles in national international conferences. His area of research include MIMO antennas, antenna for IoT application, circularly polarized DRAs, ultra wideband and super wideband antennas, wearable antennas, antenna optimization using machine learning. Dr. Sharma is working as an expert reviewer for several international journals of various reputed journals such as IEEE Transaction on Antenna and Wave Propagation, IEEE Antenna and Wireless Propagation Letters, AU International Journals of Electronics and Communication Engineering, Microwave and Optical Technology Letters, and many more. He is also doing some research projects which have been funded by SERB New Delhi and CST UP, MHRD New Delhi, and his name is also included in the list of world ranking of top 2% scientists. In 2021 in a database which was created by Stanford University USA 2021. So I request sir to come on the dais. Before coming on the dais, I request Mr. Sikandar sir to please welcome sir with a bouquet. Thank you very much, sir.
Okay. So, very good morning to all of you. First of all, I am thankful to the organizer, Dr. Prasant Pandey sir, Dr. D.K. Tripathi sir, Vikas Tiwari sir, Sikandar sir, and the entire REC family, REC Sonbhad family, because I was also the part of this family in 2017 from 2017 to 2019. After that, I have joined the MNIT. As the title actually, this program having actually based on the emerging trends in photonics. So I will talk on this the same you can say that which is in line to this FDP title, that is the design challenges. What are the challenges when we design? Because right now when we are talking about the 5G and beyond communication, or you can say that in several countries we are also talking about the 6G. 6th generation communication. So the basic fundamental of this all these generations are it is actually the frequency of operation is moving towards the higher side. Okay, it is moving towards the millimeter wave communication, which is more than 40 gigahertz, or it is also moving towards, in 6G we are going towards the optical domain, we are going in a terahertz regime. Okay, so what are when we increase the frequency of operation, then there are several benefits of that, because as per the as a undergraduate student, if all of you are knowing about the Shannon's capacity formula. According to the Shannon's capacity formula, you can increase the data rate of the communication system either by increasing the bandwidth or by increasing the SNR, signal to noise ratio. Okay, so when we are moving when we are moving towards the higher frequency side, then obviously the bandwidth is increasing. Let us talk let us take one example, that if I am talking that one of the communication system is working in between 1 to 2 gigahertz and another communication system is working between 1 to 2 terahertz, so obviously the bandwidth is higher on the terahertz regime, it is 1 terahertz bandwidth. So according to the Shannon's capacity formula, the bandwidth is increasing, the capacity is increasing with the enhancement of the bandwidth. Or the second type, or second, you can increase the capacity by increasing the signal to noise ratio. Okay, we will discuss later on in this presentation how we increase the SNR by using the MIMO communication system. Okay, so as you increase the frequency, there are lots of challenges arises when you design an antenna. Okay, when you design an antenna, there are lots of challenges occurs as you increase the frequency of operation. Like let us suppose that we have a metallic antennas around us, we have a patch antennas, microstrip antennas. Okay, so these are the metallic antennas, and there is a skin effect concept comes into the picture, and skin effect is more dominant as the frequency is increasing. Okay, so as the skin effect is more dominating, so more and more losses are occurs and the antenna gain reduces. As the frequency increases, the antenna gain is reduces due to the skin effect in case of the metallic radiator. So we have to design an antenna that does not have any metallic part. Okay, when you increase the frequency of operation. So these are the outline of my presentation. Initially I started with the introduction, what are the advantage. However, I have discussed all these things, what are the characteristics of terahertz waves, what are the different categories of terahertz antennas. Okay, and then we will move towards the what are the new research areas in the terahertz frequency regime in case of antenna design. Okay, so now as I already discussed that we are basically, as we move from one generation to the another, from 5G to 6G, then the main focus is on the data rate. It is moving from GBPS to TBPS. Okay, another thing is that in terahertz are widely used in medical applications. Okay, however, it is also used in wireless communication right now. Right now we are also working on terahertz frequencies also using in the communication field, wireless communication field. It is initially it is used widely used in imaging process, because wavelength is very shorter. Okay, so so we have a, it is widely used in imaging applications. It is also used in medical field, sensing, medical sensings. Okay, so now what are the characteristics of terahertz waves? So we have, as compared to X-rays, we have a less damage in case of a terahertz frequency. At terahertz frequency, I already discussed this thing, that the terahertz waves having a wider impedance bandwidth. As I already discussed that thing, if you are comparing with the gigahertz frequency range, you got a good bandwidth, a wider bandwidth in case of terahertz communication system. It also having high spectral resolution. Terahertz waves can penetrate through some non-metallic, non-polar materials of shorter wavelength. So that's why it is widely used in imaging process. Okay. Now the categories, there are 3 categories. We have divided the antennas for terahertz regime is divided into 3 categories. One is a metallic antenna, another one is a dielectric antenna, and third one is graphene based antennas. Okay, so this is the new category, and one more category is there, and which is the combination of these two, which is the combination of dielectric as well as graphene, that is known as a hybrid antennas. Okay, so here we have 4 categories in the slide. There are 3 categories are showing, but actually we are divided the terahertz antenna into the 4 categories. Okay, one is a metallic antenna, another one is a dielectric antenna, that is also called as dielectric resonator antenna, and the third category is graphene based antennas, and fourth category is the combination of these two, dielectric resonator and graphene, which is widely used right now. The combination is widely used, dielectric resonator and the graphene. Why it is used, we will discuss later on. So the metallic antennas, what are the metallic antennas? Actually we are using the main thing is that if you are designing the microstrip antenna or a patch antenna at terahertz frequency, then its gain is very less. It is a low gain antennas actually at microwave frequency, while it becomes very less, it having a very less gain at terahertz. It is going towards minus 20 dBi. Okay, so we cannot use such type of antennas in optical domain. Okay, so some of the authors or researchers have designed the horn antennas. Horn antenna having a characteristics, you can say that horn antenna having a very high directivity. There is a relation between directivity and the gain. Is D is directly proportional to directivity. Okay, as the directivity is increases, the gain also increases. If you study the antenna and wave propagation through Balani's, C.A. Balani's book is there. So in case of there is a relation is given there, that gain is directly proportional to the directivity. We have a radiation efficiency, G equals to neta into D. So in case of a microstrip antenna, the radiation efficiency is decreases drastically. Okay, and the directivity is also not very high for microstrip antenna, that's why its gain is very less. Okay, while in case of a horn antenna, the directivity is very high, however there is a radiation losses, neta is also less in case of a horn antenna because it is also a metallic antenna, but because of the directivity is very high, that's why its gain is good. Its gain is around 20 to 30 dBi, and also I don't know how many of you are aware with the cross polarization label, but horn antenna also having the low cross polarization. Cross polarization means in a layman language you can say that it is a wastage of energy. If it is a linearly polarized antenna, okay, it is a wastage of energy. So in case of a horn antenna we have a low cross polarization. That's why some of the researchers have developed the horn antennas in the terahertz frequency regime. Okay, but there is a problem with the horn antenna. You cannot use the horn antenna with your communication system which is compact in nature. Okay, we are basically design the horn antennas for radar communication system, for antenna testing purpose, because it is bulky in nature, or it is bulky in its mechanism is bulky. Okay, so we cannot use such type of antennas in a compact communication system. Okay, so next thing is that when we are talking about the antennas for terahertz communication, we are basically focused on the frequency tunability. Okay, we cannot achieve frequency tunability in case of a metallic antennas. Okay, there is a problem that actually the frequency tunability, in order to achieve the frequency tunability, we are basically it is based on the pin diode active element, that is pin diode or a varactor diode, because in case of a varactor diode, as we change the reverse bias voltage, the capacitance, its capacitance is changing. As the capacitance changing, resonant frequency is shifting from one frequency to other frequency. While such type of pin diode and varactor diodes are not available in a terahertz frequency domain, so frequency reconfigurability cannot be achieved in case of metallic antennas at terahertz frequency. First thing is that. Second, now we will move towards the dielectric resonator. As I already discussed this thing, that the gain is less in case of a metallic antennas. So we will move towards the dielectric resonators. Okay, actually the resonators basically, if you see, how many of you are aware with the cavity resonators? Cavity resonators सबने देखा होगा. Cavity resonator क्या होता है, रेक्टेंगुलर वेव गाइड की तरह होता है, और उसको या तो एक एंड शॉर्ट करते हैं, एक एंड ओपन रखते हैं, या दोनों ओपन रखते हैं, दोनों शॉर्ट रखते हैं. अगर आपने आरएफ माइक्रोवेव लैब की होगी तो यू हैव सीन द कैविटी रेजोनेटर. इट इज बेसिकली यूज्ड टू स्टोर द ईएम एनर्जी, because there is a impedance mismatch, na, there is a impedance mismatch, so some standing wave are created between these two walls. Either it is a open circuit, short circuit, or both are short circuit, both are open circuit. So according to that we have a different types of cavity resonator, that is the metallic resonators. Okay, the metallic resonator, however, there is no radiation losses in metallic resonators, but its bandwidth is basically, you can say that fixed. Its bandwidth is fixed. Cavity resonator having a fixed bandwidth. Okay, this is the problem with, and its quality factor is also fixed. You cannot increase or decrease its quality factor. That's why in 1939 a US based scientist, that is Professor Richmeyer, developed a structure that is based on the ceramic material, in 1939, and that is used for storing the EM energy. Okay, so we have two different types of resonator. One is a metallic resonator, another one is a dielectric resonator. What is the difference? What is the advantage of dielectric? Why we move? Because cavity resonator having its own advantage, but why we move towards the dielectric resonator? The reason is that in case of a dielectric resonators, you can increase or decrease the quality factor very easily. Okay, as you increase the permittivity of the material, the quality factor is increasing. What is the quality factor? Anyone aware with the quality factor? Quality factor is basically it is a parameter that is used to define, or it is used to signify the how much power is storing. Okay, as the quality factor increases, that means more energy is concentrated, more energy is stored in the device. Okay, so or there is one more thing. As you see, there is a relation between quality factor and bandwidth. Okay, there is an inverse relation between bandwidth and the quality factor. As the quality factor is increases, bandwidth is decreases. There is an inverse relation. Okay, as the quality factor increases, bandwidth decreases. Bandwidth decreases means what happens? The band is becomes narrower. ठीक है, तो जब बैंड नैरोअर होगा तो क्या होगा? अब वाइड बैंड है अगर मेरा एंटीना, इस तरह का रेस्पॉन्स है, ठीक है, और एक रेस्पॉन्स ऐसा है, तो क्या होगा? दैट मीन्स योर सेलेक्टिविटी इज वेरी हाई. व्हेन यू डिजाइन अ फिल्टर or a oscillator, then we are talking about, we are basically focused on the selectivity part. Selectivity आप सबने पढ़ा होगा, आई थिंक बेसिक इलेक्ट्रॉनिक्स और इन सब में पढ़ाया जाता है कि what is selectivity. When you design a filter, we actually see the role of factor. रोल ऑफ फैक्टर देखते हैं ना, जब कोई भी लो पास फिल्टर या बैंड पास फिल्टर डिजाइन करते हैं तो वह रोल ऑफ फैक्टर क्या बताता है? कितना, अगर रोल ऑफ फैक्टर कम होगा तो क्या होगा? इन दैट केस, if the roll of factor is decreasing, that means your filter characteristic is going towards the ideal characteristic. फिल्टर क्या है? फिल्टर आइडियल, जैसे अगर मैं कहता हूं कि आई हैव टू डिजाइन अ लो पास फिल्टर, तो उसका फ्रीक्वेंसी रेस्पॉन्स कैसा होना चाहिए? फ्रीक्वेंसी रेस्पॉन्स कैसा होना चाहिए लो पास फिल्टर के लिए? ऐसा होना चाहिए आइडियल लो पास फिल्टर के लिए, बट ऐसा होता नहीं है प्रैक्टिकली कैसा होता है? देयर इज सम स्लोप देयर. ठीक है, इफ द रोल ऑफ फैक्टर इज डिक्रीजिंग, दैट मीन्स दिस स्लोप इज डिक्रीजिंग एंड योर फिल्टर बिकम्स मोर एंड मोर इज मूविंग टुवर्ड्स द आइडियल. ओके, तो अब यहीं पे आ जाते हैं दोबारा से, इसके जो मैं बेनिफिट्स बता रहा था कि व्हाई वी मूव टुवर्ड्स द डाइलेक्ट्रिक रेजोनेटर. तो as I increase the permittivity, that means we are decreasing the quality factor. Okay, we are increasing the quality factor. As the quality factor is increases, bandwidth becomes narrower, and the bandwidth become narrower, so its selectivity is more. That means it is moving towards the ideal characteristics. Your filter is moving towards the ideal characteristics. This is the advantage of dielectric resonator. In case of cavity resonator, there is no such type of case. Here, in case of a cavity resonator, we have a fixed quality factor with response to the frequency, resonant frequency. Okay, so or its dimension. Quality factor in case of a metallic resonator, it depends upon the dimension of the waveguide as well as its resonant frequency. Okay, it does not depends upon the material. Okay, while here the quality factor depends upon the material. Okay, it depends upon the permittivity. As the permittivity goes on the upper side, then its quality factor is higher and its selectivity is higher. That's why such type of structure is widely used by ISRO right now. Okay, dielectric resonators are widely used by ISRO to design the oscillators and filters of high selectivity. Okay, so Richmond developed in 1939. Richmond developed this concept dielectric resonator for designing of filters and oscillator. He was not design the dielectric resonators for antenna case. He was designed this dielectric resonator for designing of filters and oscillators. Okay, 1960 it is practically used. Such type of structures are practically used for designing of microwave filters and oscillators. Now, but there is a problem. There is a problem with dielectric resonators. What are the problem? Problem is that actually if I don't know how many of you are aware with the optical waveguides, that is also known as dielectric waveguides. ऑप्टिकल फाइबर कम्युनिकेशन पढ़ा होगा तो उसमें ऑप्टिकल वेवगाइड पढ़ाया जाता है. तो in optical waveguide we have two different types of mode patterns. Okay, one is known as a confined mode, another one is known as a non-confined mode. Okay, in case of a confined mode, all the electric energy is confined inside the structure. ठीक है, और very less amount of energy is going in the environment. Okay, because if you see that boundary conditions of metallic waveguide, metallic air की boundary conditions क्या होती हैं कि tangential component of electric field is 0, ET is equals to 0, because none of the power is going in the from metal to the air. ठीक है, उसको क्रॉस नहीं कर सकता ना. जैसे ये मेटल एक बाउंड्री है, यहाँ से ईएम वेव आएगा तो क्या होगा, यहाँ से रिफ्लेक्ट होके चला जाएगा, इसके बाहर नहीं जा सकता, नहीं जा सकता ना. तो क्यों नहीं जा सकता, क्योंकि बिकॉज द टेंजेंशियल कंपोनेंट ऑफ इलेक्ट्रिक फील्ड इज 0, E10 is 0. While this is not the case in case of a dielectric waveguide. In case of a dielectric waveguide, this boundary is not perfect. That means the tangential component of electric field ET is not equals to 0 for dielectric air boundary. It is 0 for dielectric metal boundary. ठीक है, तो क्या होगा, तो that means there is some losses of EM wave. अगर मैं कहता हूँ कि ये this is the metallic plate, this is the metallic plate, तो यहाँ से जब EM wave यहाँ strike करेगी तो यहाँ से कहाँ चली जाएगी, ऐसे. But in case of a dielectric, some energy is going in this direction, तो कुछ तो इससे क्रॉस कर जाएगा और कुछ क्या हो जाएगा, इस डायरेक्शन में चला जाएगा. दैट मीन्स देयर इज सम लॉसेस. जितनी एनर्जी हम ट्रांसमिट करना चाह रहे थे, वेवगाइड के केस में क्या होता है, एनर्जी कैसे ट्रांसमिट होती है वेवगाइड के केस में, वी हैव अ टू प्लेट्स, मेटालिक प्लेट्स, एंड द EM wave is striking on this surface, then again on this surface, then again on this surface. ऐसे ही होता है. ठीक है, because we have a tangential component is 0, so entire EM wave is transmitting from source to load. Okay, while in case of a dielectric waveguide, some energy is coming from this side and strike on this boundary. So some part of the energy is going on this direction, but some part is going outside this dielectric. Okay, so there are some losses, and that type of losses are known as radiation losses. रेडिएशन लॉसेस हो गए ना. जो चीज हमको कन्फाइन करके रखनी थी वो कन्फाइंड नहीं हुई पूरी तरह से, वो क्या होगा, कुछ तो कन्फाइंड हुई और कुछ क्या हो गया, बाहर एनवायरमेंट में चली गई. ठीक है ना. तो this is the drawback of if you are designing the or if you are using the dielectric resonator as a filter or oscillator or a waveguide, then this is the drawback of dielectric resonator. एडवांटेज आपको समझ में आया था. एडवांटेज क्या था कि हाँ क्या था, हाँ यस, as the because the quality factor is more and more in case of a dielectric resonator, as you change its material, so its characteristic becomes more ideal. ठीक है, it is moving towards the ideal characteristic, but there is a drawback also. Drawback is that there is some losses of EM waves in case of a in case of a dielectric resonator. Now to remove this problem, we are using the metallic cavities. We are using the metallic cavity over the ceramic material, Okay, due to this metallic cavity, none of the wave is going in the environment. Okay, it is used for when we use the dielectric resonator for designing of oscillator and filters. Okay, after that in 1983 a US based researcher this is the entire team of Professor S.A. Long. These two are the students of S.A. Long, McClaster and Sen, L.C. Sen. They experimentally proved that as you reduce the dielectric constant of material or dielectric material, if you reduce the permittivity, as you reduce the permittivity, these losses are more and more, these radiation losses are more and more. क्योंकि जैसे जैसे आप डाइलेक्ट्रिक कांस्टेंट कम करेंगे वैसे क्या होगा, जो कन्फाइनमेंट है इलेक्ट्रिक एनर्जी का, कन्फाइंड जो इलेक्ट्रिक एनर्जी हो रही है वो क्या होने लगेगी, लॉस होने लगेगी. ठीक है, वो लॉस होने लगेगी तो रेडिएशन लॉसेस आर मोर. ठीक है, और एज द रेडिएशन लॉसेस आर मोर देन द सच टाइप ऑफ स्ट्रक्चर आर मोर लाइकली टू बी एंटीना. ठीक है, इट इज नॉट यूज्ड फॉर फिल्टर and oscillator design. So these they have removed the metallic cavity over the resonator and reduced the permittivity of the material, so such type of structures behave like a radiator, and that is known as a dielectric resonator antenna. Okay, the dielectric resonator antenna have a lots of advantage. Okay, we will discuss later on what are the advantage of dielectric resonator antenna. So they have developed this concept or experimentally proved this concept in 1983, and after 2000 and right now it is widely used in commercial applications. Dielectric resonator antennas are widely used. Okay, I have already discussed this thing, that how the dielectric resonator antennas are used as a metallic or antenna element. So first we excite this structure. This is a ceramic structure, this is a dielectric material. Okay, dielectric material. This is a dielectric material. We have excited this dielectric with the help of a probe or with the help of a slot. Then some electric field is created inside this structure. It depends upon the what type of mode is created, what are the actually how the EM energy is confined in this structure. It depends upon the modal pattern, either it is a TE mode, TM mode or a hybrid mode. Okay, so some of the energy is generated from this side and strike on this surface and again bounce back to this side. Okay, but as I told you that this is not a perfect boundary, so some of the EM waves are losses from this structure and that is used for a radiation purpose. Okay, this is the simple phenomena. However, there are lots of mathematics behind this, but simply you can say that in this way the dielectric resonator acts as an antenna. Now come to the advantage part. What are the advantages? However, it is bulky in nature. Okay, there is a ceramic material as compared to the microstrip antenna or compact antennas, it is bulky. Okay, but in current scenario there is a lots of advantage of this type of structure. First is that because there is no metallic part in a radiator, there is no metallic part, the entire is a ceramic material, so it having a high radiation efficiency and its gain. Okay, because G is equals to neta into D, so because there is no metallic losses, so the radiation efficiency is higher. As the radiation efficiency is higher, its gain is also higher. Again, second an important advantage of DRA is it does not have any surface wave. It does not have any surface wave. What is that surface wave? Eh, have you ever seen the microstrip antenna? किसी ने कभी देखा, पता नहीं देखा होगा, but there is a metallic plate, and then we have a dielectric, and then we have a metallic radiator. Okay, metallic part, and in between metallic there is a dielectric, just like a capacitor, two parallel plate capacitor. Okay, so and the radiation in case of a microstrip antenna occurs due to the fringing fields. What are the fringing fields? Fringing fields is that the wave is generated from here, EM wave, and move towards the air, and then comes to the dielectric and terminate on the ground plane. As the EM wave move from the air to dielectric, if it is moving from air to dielectric with the critical angle, then the total internal reflection, TIR, comes into the picture. As TIR comes into the picture, that substrate behaves like a dielectric. It behaves like a dielectric. That means when the wave enters into that, and it is moving, and at the edges the wave is scattered into the different direction. So the overall gain of the antenna become less, because we are trying to focus the energy in some particular direction, while it becomes scattered in different direction. Okay, so this is the problem with the microstrip antenna, while that is this type of case does not occurs in case of a DRAs. Okay, now another important advantage of dielectric resonator antenna is that it having you can control its size and bandwidth by simply changing its material, because the size of the DRA is directly proportional to lambda and inversely proportional to root epsilon r. Okay, so as you increase the frequency, its size becomes lesser. Okay, as you enhance that permittivity of the material, then again the size becomes lesser. Okay.
Anand sir, but in a 5G case, the bandwidth changes
Huh.
from 5 megahertz, 20 megahertz, sometimes
Huh.
100 gigahertz.
Huh.
If we go for the millimeter wave,
Huh.
है ना? So if our requirement is for the large bandwidth, then how we can change the material of antenna?
You can change it. Actually, the जो bandwidth is depends upon the quality factor of a radiator. Bandwidth is inversely proportional to the quality factor. As you reduce the quality factor, the bandwidth is increases, and the quality factor depends upon the material characteristic of the antenna. As you reduce the permittivity of the material, the quality factor is reducing and your bandwidth is increasing.
And how we can reduce the permittivity?
You have to change the material.
So permittivity is the natural thing. So if we have a fixed antenna, we have to change
No,
material.
then suddenly you have to design a smart antenna. Then in that case, okay, then we are moving towards the reconfigurable antennas. Okay, in reconfigurability we are using the pin diodes or varactor diodes, okay, to shift the band of operation dynamically. Okay, but as I discuss here, it is not a dynamic case. You have to give the requirement, what are the bandwidth requirement, what are the frequency requirement of your antenna, gain requirement, then you have to design. Okay.
सर मल्टीपल बैंड्स को भी जब क्रिएट करनी है अगर पास में तो भी वाइड हो जाता है ना सर?
हाँ, तो वो वाइड बैंड एंटीना का कंसेप्ट है. यू हैव टू मर्ज द डिफरेंट मॉडल पैटर्न्स, ओके, और रिड्यूस द फ्रीक्वेंसी गैप. ओके, हाँ हाँ, क्वालिटी फैक्टर बढ़ेगा ना. हाँ, नाउ So this is widely used. Such type of structures are widely used in terahertz frequency regime, because here it does not have any metallic part. Okay, it does not have any surface wave losses, or you can also very easily you can control its size and bandwidth by changing the material. Okay, the another advantage is that it is available in different shape. So in microstrip antenna there is a fixed mode which is generated, that is a quasi TEM mode, and it having a fixed radiation pattern. If it is a rectangular patch, then we have a fixed type of radiation pattern, that is known as broadside radiation pattern. While in case of a dielectric resonators, you can generate different types of radiation pattern by simply changing the mode patterns. Mode pattern can be controlled by the feeding structure of the antenna. Let us suppose that if the transverse electric mode is generated, TE mode is generated, where we have a EZ component is equals to 0, HZ component is not equals to 0. Okay, such type of mode is created inside your cylindrical waveguide. TE mode is created inside the cylindrical waveguide. Then we got a radiation pattern which is tilted in one direction. It is tilted. It is not a broad-sided radiation pattern. Okay, it is tilted in, it is tilted to 45 degree, 35 degree, and it is such type of radiation pattern is widely used in satellite communication. Similarly, let us suppose that if we have a TM mode is generated, where HZ component is 0 and EZ component is not equals to 0, such type of radiation, such type of modal pattern create a monopole type of radiation pattern, that is null in a broadside direction and maximum towards the 90 degree. Okay, so and there is another type of mode which is supported by the waveguide, cylindrical dielectric waveguide, and that is known as a hybrid mode, which is the combination of TE and TM. Okay, such type of mode is widely used in optical domain, hybrid mode, where EZ and HZ component both are not equals to 0. However, either EZ component is more dominant or HZ component is more dominant, it depends. So hybrid, that's why hybrid mode is divided into two parts. One is known as EH, another one is known as HE. Okay, so if the hybrid mode is created inside the cylindrical waveguide, then the radiation pattern is broad-sided. In that case, the radiation pattern is broad-sided. Okay, so according to the mode, you can create the different types of radiation pattern, that is either it is broad-sided or a monopole or a tilted radiation pattern. It depends. It you can use such type of radiation pattern as per your applications. Okay, high dielectric strength. This is the another advantage of dielectric resonator antenna. That's why it is widely used in radar communications, because if you are such type of structure withstand with a high EM power, so such antennas are widely used in radar communication and satellite communications. Okay.
If surface wave flows, then there will be more losses.
They actually when you design an antenna, you have your main target is to focus EM energy in some particular direction. It is not scattered in all the directions. Okay, surface wave creates the scattering of the EM wave, because it will scattered from the edges of the dielectric. Okay, so this phenomena is not advantageous for the antenna case. Graphene is widely used right now. Graphene is widely used for designing of terahertz antennas, Actually, the graphene having a property, and that is called as you can change its intraband conductivity by simply changing the chemical potential of the material. Okay, chemical potential means simple. If you change the electrostatic voltage, electrostatic potential of the surface of graphene, then its intraband conductivity changes. It's as the intraband conductivity changes, so the antenna's resonant frequency is shifted from one place to the another place. So graphene uh, graphene material is widely used to create the tunability, to create the frequency reconfigurability. However, it's having a, because it is a conductor type of thing, 2D material, so its gain is and radiation efficiency is poor. So right now in current literature, the several researchers develop a phenomena or one type of antenna, that is the combination of dielectric resonator and a graphene. We have a dielectric resonator as an antenna, and the researchers or antenna designer place a graphene material over the dielectric resonator to create the tunability. So it provides both the advantage, such type of antenna, that is also known as a hybrid antenna, okay, where we have a ceramic as well as the graphene. Okay, the hybrid antenna creates the both the advantage. One is it gives the higher gain, as well as it provides the frequency tunability. Okay. Now come to the circular polarization. What is that circular polarization? So if you see the entire literature of antenna, then most of the researchers are focused on this circular polarization. What is the need of? We have a elliptical polarization, and there are two special case of elliptical polarization. One is known as linear polarization, another one is known as circular polarization. Linear polarization again divided into two parts. One is known as vertical, another one is known as horizontal. Similarly, circular polarization again having the two parts. One is known as a right-handed circularly polarized wave, another one is a left-handed circularly polarized wave. So if you are talking about the linear polarization, then there is one drawback of linear polarization, that you if you want to receive the maximum power, then both the transmitting antenna and the receiving antenna having the same polarization. Okay, let us suppose that if transmitting antenna is vertically polarized, linearly polarized, then the receiver receive the maximum power if it is vertically linearly polarized. Okay, if let us suppose that if it is horizontally linearly polarized, then it receives the minimum power. Okay, this is the problem with the linear polarization, that you have to place both the antenna, transmitting and receiving antenna having the same polarization. While in case of a circular polarization, actually in circular polarization, the condition is that Ex, though there are two orthogonal components, one is Ex, another one is Ey, and both having a 90-degree phase shift. Ex and Ey having a 90-degree phase shift. So it creates a characteristic that is known as antenna independency, orientation independency. Okay, let us suppose that if your transmitter is vertically linearly polarized and your receiver is circularly polarized antenna. Okay, so in case of a circular polarization, Ex and Ey are equal. That means vertical component of electric field and horizontal component of electric fields are equal, and it is having a 90-degree phase shift in space. Okay, so it can receive the power, either it comes from horizontal polarization, either with the horizontal polarization or with the vertical polarization. किसी भी पोलराइजेशन में होगा वो रिसीव करेगा पावर को उतने ही अमाउंट, because both are equal ना, Ex and Ey both are equal in case of a circular polarization. So this is the advantage of circular polarization. This is the advantage of circular polarization. Okay. Now that's why circularly polarized antenna are also used in case of a satellite communication, also widely used in satellite communication, because as you transmit, let us suppose you are transmitting a linearly polarized wave from the ground station, and it is moving or it is going from the, I know there are lots of layers of in the atmosphere. We have a ionosphere, we have a troposphere, a stratosphere. So there is a large probability that the polarization got changed. Okay, the EM wave having whatever polarization you are transmitted from the ground station, it is being changed to the, when it's reached to the satellite antenna. So that's why in case of a satellite communication we are widely use or in a satellite communication we are use circularly polarized antenna, because it provides the orientation independency. How we can generate circular polarization? So any of the circularly polarized antenna actually satisfy the two different conditions. First condition is that it the orthogonal modes are generated inside the antenna, and there is a 90-degree phase shift between these two orthogonal electric field components. So if you see this structure, this is a graphene based structure, and in the graphene based patch the authors have cut a slot, this slot, and this is a stair shaped slot. If you see there is a one sorry, there is one, here we have a vertical slot, here we have another vertical slot, and there is a size is changing.
परसेंटेज बढ़ गई इसमें, जूम हो गया है,
जो
दीपक देखो
इसको पता नहीं, एलजी वाला तो हम कर देते हैं।
बैक कर दीजिए सर, कुछ को देखिए बैक करना होता है। सर यहाँ अंडू का नहीं है, हाँ इसके बाद, हाँ ये देखिए क्या है,
दीपक आ गया होगा, इंद्रजीत आ गया,
क्या सलाह दी मेरे मन से
जूम हो गया,
ये लिखने वाला बंद कहाँ से होता है, दिखा दो, जूम हो रखा है, उसको
अभी
टेप करो, 116 100 कर दो ना,
हाँ
उसको हटा दो, वो पकड़ा गया वहाँ से,
वो ये
Select हो रखा है।
सेलेक्ट हो गया, ठीक ठीक,
वो आप ऊपर नीचे करें हो जाएगा।
इसी हो जाता है ना।
अच्छा अच्छा अच्छा, ठीक ठीक ठीक। So now if you see this structure, then there is a less length and it is having a larger length. So now we have this type of slot creates the two orthogonal modes. One is due to this one, another one is due to this one, but and also we have to create a 90-degree phase shift between these two components, that is generated by this one and this one. So in order to create a 90-degree phase shift, we are authors actually create a length difference. If you see S1 having a lesser length, S2 having a larger length, okay. So as you create a length difference, then it will create a path difference, okay. As the path difference is created, so phase difference is equals to 2 pi by lambda into path difference, okay. So now if you optimize these lengths, you can create a 90-degree phase shift between these two field components, okay. So that's why the axial ratio, which is the ratio of Ex and Ey for circular polarization, it must be equal. So the axial ratio moving towards the 0 dB within the operating band, okay, by simply changing this structure.
How author got this idea that we have to cut slot like that?
It comes from the experience. It actually there is some fundamentals that the circular polarization, we know this thing that the circular polarization is generated through by creating the Ex and Ey component, which is equal in length. So first you have to focus how we can generate the orthogonal. Let us suppose that we have another structure like this. There is a slot or S type of slot, where again the author have created the two slot or two it is not a slot, it is a notch, okay. It is a notch of having unequal length. The length is not equal, L1 is not equals to L2. So by these two notches, first the author generated the two orthogonal field component, because in case of a circular aperture, if we are talking about the circular aperture, then circular aperture supports the two different field pattern. One is along X direction, another one is along Y direction. Now you have to create a phase difference between these two field components, Ex and Ey, okay. In order to create a phase difference, we are creating a notch, or authors are creating a notch which having unequal length. So that's why the Ex and Ey component with a 90-degree phase shift, okay. Again in this is also a circularly polarized structure, and here the authors have used this dumbbell shape, you can say that dumbbell shape ceramic antenna, okay. Why dumbbell shape? Because if you create such type of structure, then its effective permittivity is lesser as compared to the cylindrical ceramic. Let us suppose that if we have a cylindrical solid ceramic, now we have created we have removed some part of the ceramic in between that. So the effect, because of this air gap, the effective permittivity, overall effective permittivity is lesser as compared to the cylindrical structure. As the effective permittivity is lesser, the quality factor becomes less and you got a good bandwidth, okay, larger bandwidth. If you see carefully this structure, then this red line is for cylindrical DRA and this blue line is for dumbbell shaped CDRA, okay. So in case of blue line having a larger bandwidth as compared to the red one, okay. This is due to the effective permittivity reduction. So again we in this structure two different resonant peaks are occurs. These two resonant peaks are due to the HEM11 delta mode and 12 delta mode respectively, okay. Again we have checked this. Now in this structure, in this if you see this structure, the authors have used the graphene layer. This black one is a graphene layer over the ceramic, okay. As you change the chemical potential of the graphene layer, then there is a shifting in the resonant peak, okay, and it will create the tunability in the structure. Now come to the another important concept, and that is known as a MIMO technology. Initially when I start this presentation, I have talked about the Shannon's capacity formula. Okay. According to the Shannon's capacity formula, the data rate of any communication system or capacity of the any communication system is increasing by increasing the bandwidth or by increasing the signal to noise ratio. So when we are increasing the frequency of operation, that we got a more and more bandwidth. While how we increase the signal to noise, because as per the government restriction, we cannot enhance the signal power. So there is a restriction of the signal power. Okay. So you have, in order to increase the signal to noise ratio, you have to reduce the noise level. Then only the SNR is increasing. Okay. So in order to reduce the noise, we are moving towards the MIMO. So again, there are two different formats in MIMO. One is known as a spatial diversity, another one is known as spatial multiplexing. In a spatial diversity, the same message information is transmitted from the different antennas, so it will improve the reliability of the communication link. Spatial multiplexing, we divide the message stream into small sections and transmit these sections by the different antennas, so it increase the capacity of the system. Okay. So this is the part of the communication. Now we have to now how can we design a MIMO antennas for in a terahertz frequency regime. Okay. So first we have to focus on the isolation. Isolation means these two ports are behave isolately. Okay. The mutual coupling is lesser. So in order to reduce the mutual coupling, we are place these two ports orthogonally. Okay. It will create the polarization diversity. As the polarization diversity comes into the picture, if you see these two lines, this is for the S21 structure, S12. Okay, S12 or S21, it denotes the mutual coupling. So if you see carefully these two curves, then for when both the ports are placing parallelly, then the mutual coupling is higher, while when we place orthogonally, the mutual coupling is lesser. Okay. And that type of concept is known as a polarization diversity. You can improve the isolation by different techniques, like we have a polarization diversity, we have a space diversity, you can change the distance between two ports. So there are lots of technique available.
Can we exploit greater than second order diversity also with such type of antennas?
Second order,
More than second order diversity.
I don't have any idea about that. What is second order diversity?
Means we get two independent paths. The
Mm,
receive wire two independent paths.
okay, okay. Acha. You can do that thing, but by using this type of structure you cannot achieve. Okay, second order diversity. Okay, you have to create the two different ports. Okay, one is for transmission and another for is reception. Now come to the another part. Actually, when we design the MIMO antennas, we are basically focused on two different types of isolation. One is known as one is based on S12 and another one is known as far field. Okay. So in this type of structure, both the antennas are radiated towards the broadside direction. So there is no far field, you can say that isolation in such type of structure. Okay. While in this structure, this is also designed for terahertz frequency domain, and here the authors have designed this antenna having a multi-directional pattern diversity. Okay, that means port 1 is radiated along this direction, along plus z direction. Port 2 is radiating along plus y. Port 4 is along minus z. Port 3 is along minus y. So each antenna is radiated in different direction, like this. If you see this, the port 1 is radiated in this direction, port 2 is radiated in this direction, port 3 is radiated in this direction, port 4 is radiated in this direction. Okay, so this is known as a pattern diversity. That means this antenna having a far field isolation. Okay, while in this in the previous antenna there is no such case. It is not having any far field isolation. It is it is based on S parameter isolation. So when you design a MIMO antenna, there are two different types of isolation. One is known as S parameter isolation, another one is known as a far field isolation. Now this is the last one from my side, that what are they actually the antenna designing in terahertz regime is very or you can say that it is a newly introduced area. Okay, right now very few papers are available in this area. Most of the work is going in between 0.1 to 10 terahertz. Okay, another important thing is that right now there are no characterization facility available in India for terahertz antennas, and its fabrication is also very costly. So most of the research articles in SCI index journals are totally based on simulation. Okay, there is no fabrication and characterization is there. So right now, if this area is you can say that emerging area, there are lots of things to do. You can do lots of things in this area, antenna in terahertz domain. Okay, so it is over from my side. Okay.
कुछ पूछना है आप लोगों को? You have any query, you may ask.
Linear polarization क्या मतलब क्या बताऊँ? Linear actually there is a polarization means the orientation of electric field. Simple, in simple language you can say that. So we have a elliptical polarization, that is the generalized case, and there is a two special case of elliptical polarization. One is known as linear polarization, another one is known as circular polarization. Now we have two different types of field, electric field. One is known as Ex, one is oriented along X direction, another one is oriented along Y direction. So if Ex and Ey both are oriented in a same plane, okay, and that type of polarization is known as linear. Okay, so if it is vertically linear, if it is oriented along a vertical direction, then it is known as vertically linearly polarized. If it is oriented in a horizontal direction, that is known as horizontal linearly polarized. Okay, so this is
Thank you, sir. Very good morning. I, Sikandar, Assistant Professor, Electronics Engineering Department, would like to thank Dr. Anand Sharma sir for such an informative and distributive lectures. Dr. Sharma sir covered use and application of terahertz and why it is very important in terms of bandwidth. Actually, today's need of communication is the bandwidth, and how terahertz supports to give bandwidth mainly depend on the two factors as explained by Dr. Sharma in a simple Shannon formula through the frequency range that is given by terahertz, and second one is reducing or improving SNR. So SNR improvement is discussed by sir through MIMO technology, where sir discussed very examples and prove how bandwidth improvements takes place through MIMO technology. And sir also discussed very basic things, metallic cavity, how and why we have moved from metallic cavity to dielectric resonator cavity, and how these resonator can be used as a radiating element, that is antenna. Sir discussed very basics and important things that actually we could not know how these disadvantage of metallic structure is used as a advantageous antenna. So sir, we are very thankful for such an informative and basic knowledge giving us, and it also motivate us to work in this field. Since we know the basics of this field, we can add in higher research, because if we don't know the basics of the field, we cannot motivate self to work in recent area, a recent research area. So now I would like to call Dr. D.K. Tripathi sir and Himanshu Katiyar sir to facilitate Anand Sharma sir. Sir, please.
Thank you, sir.
Thank you.